Okay. All right, so I think for my students over the years, this has been the hardest topic, is special right triangles. Trig, I think, is number 2. I think special right's number 1 in terms of most difficult. So let's roll through it. It won't take me that long, but I'll try to explain as I go. So this is, I think, first of 6 lessons in the unit on special rights. This one's called 30, 60, 90, and I believe that it's called maybe adj-leg or adjacent leg. And here's what we start with. What type of triangle is this? Good, right triangle. Okay, now let's add something to it. If I told you that this angle was 30 degrees here, so you know this one's 30, this one's 90. Do you know this one up here? It's going to be 60. Why? Because the 30 and the 90, what's 30 plus 90 for those two? 100 and, so we've got 30 plus 90, 120, right? We know that all 3 of the angles of the triangle are 180, so we have 180 minus the 120, what do you get? 60 degrees. So you have here the one of the magic triangles called the special right. This one happens to be 30, 60, and 90, hence the name 30, 60, 90. Does this make sense so far? So why is this a magic triangle? Because the ratios of the side lengths play out in a very specific manner every time, whether the triangle is very small or very large. Here are the ratios. This side we're going to start with a base value, and we're going to call it x. It's in a very specific position. It's the side across from or opposite the 30-degree angle. So the x just means it stands for some length. Whatever you put in for x, that becomes the length of this side. This side, the hypotenuse, the one not touching the 90, becomes 2x for this very special 30, 60, 90 triangle. Okay, so you ready? If this side were 5 long, how long would the hypotenuse be? If this side were 5 long, this is 5, how long would the hypotenuse be?
10.
Yeah, trust yourself. This one's 5. This one's 2 times it, 10. Are you with me? Okay, you good so far? Are you following this? Are you guys, I know you're doing some other things while I'm doing this, but this one's now ready for the next one? This steps up a little bit. The ratio for this side here, the one attached to or adjacent to the 30-degree angle, becomes this value. Oops, sorry. There. Thank you very much, okay? My brain says one thing and my hand just writes another. This is said to be x times the square root of 3. Everybody say x times the square root of 3.
X times square root of 3.
Another way to say square root is radical. So you can say x radical 3. Say x radical 3. So follow me around the triangle here. If this side were 5, how long would this side be up here?
10.
10. And how long would this side be down here?
5 times the square root of 3.
Everybody say 5 times the square root of 3. Okay, so far it doesn't seem that hard, right? You're like, okay, this doesn't seem that hard yet. But trust me, there's some aspects of depending on which side we're given. So this becomes the model. It's the same every time for a 30, 60, 90. And I would tell you to memorize it, but we hate memorizing things these days. But you have to know that the x value is opposite the 30. The 2x must be on the hypotenuse. And the x times the square root of 3 has to be on this adjacent or the one opposite the 60. It's that way every time. If we mix these up, then this doesn't work. It's not right. The ratios are in very specific places every time. Okay, so let's go through and do our first example. Let's do this here. Given a 30, 60, 90. Now I don't have to put 60 there. All I need to do is write a 30 and a 90, and you know that's 60. So given a 30, 60, 90. If this side is 4, how long is the hypotenuse? And this one up here is the hypotenuse, right? The one not touching the 90. Say it again. Good. And x in this case is?
4.
Good. And so the hypotenuse length is?
8.
Does this make sense? And so this becomes 8 for this specific triangle. So here's your model that you're describing, and that's very good. Here's the specific one in this case, and now the x becomes something, so therefore the hypotenuse is known. And the adjacent leg here to the 30, what is its value?
4 times the square root of 3.
Everybody say 4 radical 3.
4 radical 3.
Good. And I hear your brain going, really? And yes, that's really what it is. And you can plug this into your calculator. You just say 4 times the square root of 3. It'll give you a lot of decimals. So we leave it square root of 3. It's more accurate to leave the square root of 3 in because you don't have any rounding errors. So we leave it 4 times the square root of 3 or 4 radical 3. Okay, you good with this? Okay, let's take it up a notch. Here's where the complication comes in. Let's say we have another 30, 60, 90, so you know the ratios now. Now they tell us that this side up here is 10. How long is this side over here?
5.
Are you guys with me? Yes, but hang on. How long is this side over here? And if you're saying 5, I appreciate that. That's right. So here we went forward, right? Now we're given this, we must go backwards. Fair enough? Okay. Tell me now, take your time a second, how long is this side going to be for this triangle? Five radical 3. Was anybody tempted to say 10 radical 3? Sometimes that's the temptation, all right? But if you're going backwards, boom, 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 this makes sense to you. Does this make sense so far? Okay. Now here's the complication I promised. Let's take another 30, 60, 90. And this time, I gotta say 30 here, so we know it's a 30, 60, 90. This time we're given that this side length is 12. So just like here, when we were given 10, we had to go backwards to get to the 5. Does that make sense? Now we have to go backwards to get to this side. So we did something with the 10 that I'm going to explain in a moment. It's maybe easier just to travel down this road. If the side of the one we have is 12, and the side of the model is x radical 3, these two sides have to be equal lengths. We just want to know what the x has to be for this to work out. So here's how we do it. We say that this 12 must equal this pattern, or this ratio of x times the square root of 3. You okay with the idea that they have to be equal? As long as we know what that x is, then this is going to work out, and this, now we're going to know what x is. Whatever x has to be for this side to be 12, that's going to be what x is here and 2x is there. Fair enough? Okay, so let's solve this. First I'm going to flip it because I'd like the x on the left side. Remember, it's an equation. You ever seen those signs at a gas station that rotate around? So your equation rotates too. So the entire thing is rotating around. So this one rotates. The equal sign rotates also. It just doesn't look any different because an equals is symmetrical, right? So first thing, let's divide both sides by square root of 3. So it's gone here, and we have x equals 12 over square root of 3. The first problem with this is the idea that it's illegal to have a square root in the denominator position of a fraction. Illegal being it's not reduced. Remember in fractions, if you had 3 over 6, you weren't allowed to write that. You had to say 1/2. This is a similar situation for square roots in mathematics. We're not allowed to have a square root in the denominator. So we have to do this complicated process, well, complicated I guess, but complicated idea of a process of rationalizing the denominator. The name is a terrible name because it doesn't help us figure it out, but here's what it looks like. We're going to multiply this by 1. Square root of 3 over square root of 3. Any value over itself other than 0 simplifies into 1. So this fraction right here is 1. We're taking a fraction, multiplying it by 1. We can multiply by 1 because it doesn't change the value. If you have $1 and you multiply it by 1, how much money you got? Still the $1. Does not change the value. So this is a legal move. So we're going across the top. We're saying 12 times the square root of 3. And we get 12 times the square root of 3. What is 3 times 3?
9.
Good, 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 good. 9. And it's got the square root symbol. Sorry. Again, my brain not working. 3 times 3 is 9. And again, it's under the square root symbol. So what is the square root of 9? What number times itself produced 9? 3. So that simplifies on the bottom to 3. There's still 12 square root of 3 on the top. And 12 divided by 3 is 4. So we get to do a final answer of 4 times the square root of 3. And what were we solving for in the beginning? X. Now look back at our model. Where does x go? X is the side opposite the 30 degrees. What is x in this case, for this particular situation? It's 4 times the square root of 3. So that's the length of that side now. What do you think the length of the hypotenuse is? Louder. 2 times 4 is 8. And the radical 3 goes along with it. And it becomes 8 radical 3. And so now it fits all the ratios. This is x of 4 radical 3. If you multiply that by 2, it's 8 radical 3. If you multiply this by square root of 3, the square root of 3 times square root of 3 is square root of 9. Square root of 9 is 3. And 3 times 4 is 12. So that works out down here. The ratio works for all the sides now, again, with this expanded size triangle. Does this all make sense? So where does the complication come in? First, you've got to know the pattern. I would write down the pattern every time I was solving one of these because my brain needs to think through this. Second, depending on which side we start with, this one's easy, this one's less easy, and this one, when they give us this side only, is the most difficult, especially when we have to go through the rationalization of the denominator process to get a final answer, to simplify the answer. So depending on which information they give us, this could be a really easy problem or a really difficult problem. And then let's mix up the pattern just before we go. say they gave us a right triangle like this. And the 30-degree angle's here. Can you fill this out in the pattern of the mold right here? Can you redo the triangle? We flipped it and rotated it, right? We changed the orientation of it. Can your brain think through how this pattern fits it? For example, what's the ratio for this side?
2x.
Okay. Are you saying 2x? And you're looking at this, right? Go back to this one where your brain's trying to orient where everything is. So here's the 30-degree angle. Here's the hypotenuse. Always with the 30, 60, 90, the hypotenuse is the 2x. Where's the hypotenuse in this case? Not touching the 90, so this one's the 2x. Does that make sense? Is your brain able to sort of rotate everything around and take a second to look at it? And then what would be the length of this side here?
X.
What do you think? What's the length of this side? Okay, good. Thank you, guys. X, because it's across from or opposite the 30-degree angle. Good. What's the length of this side?
X radical 3.
X radical 3. So I think you should, get oriented in one orientation to the model, the mold, and then be able to rotate it and know where everything is. And then you're playing with different problems of what's given to see what the final answer is. Okay, good. That's all I was going to cover. Right? That's special right triangles number 1, the 30, 60, 90.